The topic is power of ensembles, and to start with, I guess I want to kind of start with a story, and this is a story I use every time I talk about model visualization or modeling to some extent. How many of you have heard the story about the blind man and the elephant? Okay, a few, not as many. So it's a very common folklore or told in many cultures, and it goes something like this: that there is 6 blind men who are brought to an elephant. So they can't see the elephant, but they're brought to an elephant, and they decide to touch the elephant and see what the elephant feels like, right? So what does it look like? And they're trying to build. So the first one goes to the elephant and actually encounters the elephant at the side, with the sturdy side of it, feels it, and says an elephant is definitely like a wall. Right? The second one actually reaches for the face and ends up grabbing the smooth tusks of the elephant. And having seen that, says an elephant is definitely like a spear. The third one manages to grab something a little lower, which is the trunk, feels it, feels the curves on it, and says an elephant is definitely like a snake. The fourth one grabs the elephant at the knees, and seeing the sturdy stump, says an elephant is definitely like a tree. The fifth one, by that time the elephant is trying to sit down, grabs the ear, sees the fan-like structure, and says the elephant is definitely like a fan. And the last one manages to grab the elephant by the tail, and seeing it is very supple, says an elephant is definitely like a rope. So 6 men, 6 different views. I like this really a lot. So these men of Hindustan disputed loud and long, each in his own opinion exceeding stiff and strong, though each was partly in the right, all were in the wrong. And to some extent, what we're trying to do with machine learning is trying to build a data-driven view of the world, right? So, and the data is, as I say, a clue to the end truth. We're trying to, and it's kind of like the elephant in the room. And we are trying to build models, right? To try and understand what it is. And as George Box said, all models are wrong, but some are useful, right? So with the model abstraction that we're trying to find out is potentially not accurate, can never be accurate, but can potentially be useful, right? And Bhargav and I have like our own take on this since we've adapted it to the ensemble talk, which is all models are wrong, some are useful, but maybe the combination of them can be better, right? Not the best quote, but that's the essence of the talk, right? So we're trying to build many models together and see if we can improve our understanding of the world through the data-driven lens that we're trying to look at, right? So what is ensemble? A group of items viewed as a whole rather than the individual, right? So if each of the blind men had managed somehow to put their model together, maybe they would have come closer to what an elephant really looks like, right? How many of you have done any kind of ensemble modeling or any kind of ensemble modeling? Okay, very few. Very few. Okay, so let's start a little bit from the back so that we kind of understand the process in the ML process, and then see where this fits in, right? So the ML process, irrespective of what you're trying to achieve, typically has these 7 steps. You start with problem definition, you frame the problem, you go and acquire the data, you refine it, so clean it up, data wrangling it, then you transform it, because the data may not be, the way it is measured may not be the way that you want to model it, so you would do what is called feature creation, and you may then explore the data visually to say, okay, what features do I want to select, model it, which will include model selection, model evaluation, and then once you model it and figured out this is the model I want to use, you will communicate it, right? So communicate the model. or communicate the solution to make that change happen that you want to with that problem, right? That's kind of the process of machine learning. For our purpose, though, we'll kind of thin it out a little bit, right? And we'll look at this representation of it, right, which kind of captures the modeling part of it, right? So we have the data space, which is the number of observations. We have the feature space, which is the number of columns, let's say. So in a typical data frame, number of observations, F being the number of features. And then we have a model algorithm that we're trying to apply to this problem. And we have some model parameters for that, right? Does that make sense? Right? So data space, feature space, model algorithm, model parameter, right? And this helps us a bit because what we're really trying to do in machine learning is search through an hypothesis space to find a suitable hypothesis that will help us predict from the problem, right? So we have an infinite hypothesis space, and we're trying to find one hypothesis that is most accurately or closely allows us to predict that process or phenomena, right? And in this model that we just talked about, the data space, the feature space, model algorithm, model parameters, model algorithm along with the model parameter is the hypothesis that we're trying, or the hypothesis space. And this is inherently infinite, right? This is a large infinite set of hypotheses, and the challenge that we have is really around how do we efficiently search in this hypothesis space, right? That's what we're trying to do. And most of us would, who start onto this machine learning, obviously start off with some domain experience, some problem definition, and have a limited set of hypotheses, and we use that, right? What we're trying to now see is, can we build on that and go further than that, right? So can we search this space much more efficiently than we would do that we're trying to do right now with using ensembles, and we'll come to that, right? Does that make sense? Yeah? Okay. Okay. Now, I'm very visual, and in order to communicate this, let's take an example. So it becomes easy for us to follow through how this is building up, and how could we actually navigate this ensemble space, right? So let's take a very illustrative example. This is a binary classification we're trying to do. So we have two classes. We will have three features, x1, x2, x3, and we have about 1,000 observations, right? So this is a synthetic data set, but it's good enough for us to understand the space of ensembles, right? As we would visualize it. So this is how the data looks like, x1, x2, and x3. And three-dimensional visualization, we can see that it's not that easy to separate. It's not definitely linearly separable. So there is probably scope for it probably is going to be harder to find the right hypothesis set for this, right? Now, building all the visualizations on 3 dimensions is going to be hard, so I'm going to make it a little bit easy for myself. And we'll do a PC on this and get 2 dimensions, which is PC1 and PC2, right? So this is how those data points look like, again, on PC1 and PC2, which is principal component 1, principal component 2 for that data set. Okay, so far with me? Nothing much. We've done 3 features, 2 classes. We've got 2 dimensions, PC1 and PC2, right? So this is the approach we're going to use across our exploration of this topic. We will train a model. We will predict the probabilities of each class. We'll score that model on one parameter, so we're choosing AUC. We could choose anything, but AUC is a pretty good one. And we'll score it via 5-fold cross-validation, right? And once we've done that, we will show the decision boundaries. Okay, so train the model, predict the probabilities, score the model on AUC via cross-validation, k-fold cross-validation, and then show the decision boundaries, right? So let's start. So we'll start with a simple model with different features, right? So as we investigate this, we'll take 100% of our data. We will choose two combinations of the features. So x1, x2, x2, x3, x1, x3. And then we also have PC1, PC2, because we created these new two features. So we'll look at those two. And we'll start with a very simple model like we would do normally in machine learning. You start and build a very simple model. So this is logistic regression with model parameter regularization C is equal to 1. Okay? And this is how they would look like, all the four combinations. Right? So we have all the four combinations. So they're 2 by 2s. And we can see the linearly separable lines. Right? So the color is the two classes on the extreme, which are clearly more on the maybe 95 to 100% scale, which is really the yellows and the purples. And in the middle are all the probabilities shaded between yellow and purple. Right? Does that make sense? Yeah? To everyone? Yeah? OK. So this is how it looks like. And we can see already that these are four possible models that we can choose with. And they give us some AUC. Right? They give us AUCs in which clearly the x1, x2, and the PC1, PC2 are on the higher side. The AUC is written on the bottom of the chart always, on the right bottom. Okay? So what would we do next in a typical process? We will tune the parameters. Right? So once we have a model, let's say we want to stick to PC1, PC2, we will tune it. And we will choose some model parameters and work through them. So C equal to 1, C equal to e to the power minus 1, minus 3, minus 5, right? This is what we would do. We would start tuning the parameters, or now, to use a buzzword, hyperparameters, but that's what we're trying to do, right? And we would get, again, a representation with a slightly improved AUC in some cases, or in this case, actually, C is equal to 1 is the best one for this 4-grid search that we're trying to do, or not a grid search, but a linear search, line search. But for these four parameters, this is what we have, right? Does that make sense? Yeah, so far with me? OK, and you would not make just one model, right? So we have logistic model. We've done some parameter tuning on it. But we would actually make maybe 2, 3, 4, 5 models, right? So let's add the model space. We will add an SVM linear, which is easy to do in this case. Scales OK at 1,000 points. We'll add a decision tree to it, and we will add a k-nearest neighbor classification, right? And now you can see this is how the classification probabilities look like. Not surprising, the SVM linear is quite similar to linear logistic. If we had gone for an RBF, we would have got much better accuracy, but linear is very similar to logistic. Decision tree, as you would see, overfits. And you can see the overfitting, the extent of overfitting, and it has a much lower AUC, right? K-nearest neighbor is doing still better, though, doing better, right? Does that make sense? Yeah? OK. So far, we've done what we would have normally done in a machine learning process, right, that we would do. Build one model, tune it, and try and build many models. And actually, we need to do all of that. We may have to tune each of these models also on that, right? Because that's how we will find it, right? So what's the challenge? The challenge here is that this process is exhaustively impossible, right? We cannot continue to search through this and exhaust all the options that are there and search through it, right? So because we're trying to search the entire hypothesis set, this is really hard. And you can obviously use human IQ, like our domain knowledge or your understanding of the domain, to try and navigate this much more smartly. Here we're talking synthetic data, but if you bring in domain, you will probably have much more ideas about what to do with the features, what to do with the models, and you can play with that, right? But what we want to do with Ensembles is find a clever algorithmic way to navigate this solution space, right? So how can we use compute as a way of proxy for human IQ to some extent? Right? I'm not saying this is either or situation. We're trying to much more navigate this space than we would otherwise have done, right? So this brings us to Ensemble. And the goal of Ensemble is really, can I combine predictions of several base estimators or several estimators, which could be from one algorithm or multiple model algorithm, so that I can improve my generalization and robustness of the solution, right? So I want to move up this hierarchy. Instead of playing with one variables, one models, I want to move up this by combining many of these estimators, right? And that is my idea, that I could actually start to navigate, get closer to a more robust and general solution, right? That's the purpose of machine learning. I want to get a solution that's much more generalizable, right? And fitting with one model may overfit, so I want to explore the space where combining models gives me better generalization. Yeah, does that make sense? Yeah, okay. So what's the ensemble approach we can do? We had data space, feature space, model space, and parameter space, right? And we can combine these three, play with different aspects of this, and cleverly aggregate them to try and find out what the solution could be, right? So how could we do that? There are 4 basic approaches to do this ensemble, right? So one is averaging, the second is boosting, the third is voting, the fourth is stacking, right? And what we'll do in the rest part of the talk is just go through each one of them and at least understand the basic intuition around each one of them. And then you can use that and apply it in your context that you're trying to do, right? So averaging, the basic idea is that we want to take these several estimators and then average them to reduce model variance, right? The idea here is to reduce model variance by averaging them out, right? So we know that if we have one good model, if we average, or if we have many good models, if we average them, we reduce the variance of it, right? How can we do that? How can we do that? We can definitely play with our feature space and data space to start with, right? So if you have your feature space, as we said, on the columns, the data space on the observations, you can do 4 combinations of that, right? You can choose only a set of observations, so a sample of observations, and that's called patching. You could choose them with sampling, so that'll be called bootstrap or bagging. Sorry, it's called bagging, so bootstrap aggregation. So if you sample them with replacement, then it's bagging. You could actually choose a set of features only, so that's a random subspace. So you're only focusing on a set of features. Or you could actually combine both of them and choose a patch. So it's a random patch. So some observations and some, right? This is 4 different approaches, valid for any kind of classifier. It's a meta classifier in that way that you can apply it to any kind of classifier inside it, right? So you can take this average approach to any particular model, right? So let's go back to our data set or our representation. What we will do is take a 50% sample, random sample, with sampling, without replacement, with replacement, and then take 50% of the feature set, and then take 50% of this data set and 50% of the features. So we get all the 4 combinations that we talked about, right? And we're still applying it on decision trees, and we can start to look at how this looks like, right? Not hard to see why we're getting straight lines in random subspace and random patches. Anybody, any guesses why we're getting straight lines? We can see stratifications there, right? Because we're taking 50% of our features, then we're basically left with one feature. What we're coming back with is lines, right? So we're using basically lines to classify. And since we can choose any feature randomly, we get lines which are vertical and we get lines which are horizontal, right? Right? And if you were to look at the AUCs, you'll find that actually patching and to some extent bagging actually does much better than random subspace and random patches, right? And that's why you find that bagging actually is a much more commonly used generalized algorithm than the other 3, at least practically experientially, right? Because we find that bagging gives us bulk of the benefit of this averaging process rather than actually going down patching random subspace or random patches, right? Does that make sense? Yeah? Okay. I like this visualization because at least you get some intuitive sense around what's really happening, right? What's happening in the algorithm, at least in this limited subspace. Okay, you can obviously extend it, and we're obviously doing averaging, but if you were to take the same trees and extend it and split the trees amongst random features, so best split amongst random features, so doing still bootstrap aggregation, but add this one more aspect that every time you have the option to split, you choose the best split amongst the features, then you get random forest. And if you actually do even more, that you don't choose the best split, but you choose a random threshold every time, you get an extremely randomized tree, right? They're all kind of adding more perturbation to our model space, right? So now we've actually moved just from the feature space and data space to also playing with the model space. It's no longer a simple decision tree. It's a slightly more decision tree plus plus, right? And I should probably have mentioned that a little more clearly. But we're basically the R split and R split at threshold, which we see in the last bottom ones, which says random split and random threshold, actually gives us something which is slightly more different than a decision tree, right? It is still a decision tree, but we're trying to make it even more random, right? Allowing us to reduce the variance when we start to aggregate it, right? And you can start to see that this traditionally starts to perform much better. So random tree forest traditionally performs much better. This is only for 10 estimators, so we're only making 10 trees and aggregating it. So we don't see that much of the efficiency. Typically, it'll be about 400 trees. Also, we're only using 2 features, right? So if you had more features, this would perform much better. And extremely random trees are, because we don't have to be so clear about thresholds, we choose the threshold randomly, they're really fast to run. So even though random forest will runs decently fast, because you can parallelize it, extremely random tree runs even better when you try to do that, right? So in this case, however, I think bagging is the one that's doing much better, right? Did I get that correctly? Yeah. Yeah? Bagging is still doing much better than our case. So averaging a strategy that you can extrapolate across feature set, data set, and even beyond, okay? Next concept is boosting, right? Now, so far we were making decision trees which were fully built up and then trying to aggregate them, right? Average them. Boosting works a little differently, which is we build trees sequentially and then try to reduce the bias, right? So the last one was really reducing variance. This one's really reducing bias. Because as we build them sequentially, we try to combine several models to make a powerful ensemble, right? So a slightly different concept, a little more harder to explain. It's not like a neat diagram to explain how this tree is built up. But you can think of this as when you have the first separation that you're trying to do with a tree, and in this case, let's say we're making only one separation. So the stump of the tree is only one, depth of the tree is one. We choose the first separation, and then we see the errors, which is in the second one highlighted with the bigger circles, the bigger reds and the bigger blues. And then we choose a separation which tries to minimize that error, right? That's how boosting works, right? So the boosting is a slightly more different way of ensembling, that we actually progressively try to work on the errors of the first tree and then the errors of the second tree and the errors of the third tree, right? So conceptually a little different, but in essence still an ensemble technique, because we are trying to build one tree on top of the other, right? We not have a simple way of weighting them, and that's why it took a long time for boosting to pick up, because it was harder to parallelize, to run it in parallel. And now that we've figured it out with XGBoost and all, it is much more efficient to run, right? So this is how it would look like. There are other boosting algorithms, so we'll run a boosting tree with different depths here. And so we'll run one which is add a boost, which is just a stump, and then gradient boosting, which slightly does it differently with, again, a stump, depth equal to 1 and depth equal to 2, right? And you can see the classification here is really different, right? Much more different than a random tree, even though the performance is actually quite good. But the way the sequential works actually is a very different way of aggregating than bootstrap aggregation. That's random forest is based on, right? I think potentially much more explainable to some extent if you'd want to try and figure out explainability of a boosting algorithm. It is potentially possible to do that, but it'll be really hard to do it on a random forest, for example, or an extremely randomized tree. Right? Okay, so far we've stuck to one model in our ensembling. We haven't played with the model space. So the second last one, actually, or the second and the third and the fourth one, both of them, use this concept of playing with different models. So right now we were just using decision trees. Now we will extend that and play with different models, right? So now we're actually ensembling some 2, 3, 4 different models that work equally well, and by aggregating them in a smart way, and there are three ways to do that, you can actually compensate for each one of theirs weakness, right? So the idea is that you have 3 good performing models, and when you aggregate them, they compensate for each other's weakness, and hence you get a better prediction, right? Does that make sense? Let's see what that means, right? So you have your data set, and you build model 1, 2, 3 to n. And each one of them gives you an output, a prediction. Once you've got that prediction, you then can use some kind of voting to find your final prediction, right? That's the idea. Now you're using predictions from different models as a way of aggregating, right? How do we do that? So now we're playing with the model space also. Earlier we were only limiting ourselves to feature space and data space and adding perturbation to the model. Now we're changing the model dramatically, right? So we could add them in 3 different ways. We could take a hard voting, which is to say whichever class has the highest mode. So if the first one is 1, the second one is 1, the third one is 0, then we choose 1 as the class, right? That's kind of hard voting. Or you could use soft voting, which is basically I have probabilities for each class, and I add them up, right? I add them up, and then or average them up, or simple average them up, and that's my soft voting, right? Now I'm playing with probabilities rather than class predictions. The third one is actually I can weight them. I can weight each of these probabilities and then come to the final score, right? Does that make sense? Yeah? So hard voting, soft voting, weight voting, right? How do I weight them? Again, everything in machine learning comes back to something else that's already done. So you do grid search. You can do grid search. You can do different operations to figure out what the correct weighting would be so that I get a better error, right? So again, applying what you would do at the first level of model, now you're applying that model validation at the second level to get weighting. Or you can do even parameter estimation based on that. So we'll come to that. But the simple idea is you can either do hard voting, soft voting, or weighted voting, right? Okay, so this is now the space looks like, right? So we choose 3 strong models. I choose a Gaussian. Now Gaussian is very strong in this case because our data was generated synthetically through something that's closer to Gaussian, right? So Gaussian performs much better even after we have randomized it a lot. We use an SVM with a radial basis kernel, and we use a gradient boosting, right? All 3 give very good performance. And now we do a soft voting on that we add their probabilities and we try and see whether the performance improves, right? So this is how the 3 look like. So the Gaussian, obviously, good performance, 0.77 on RBF, SVM also pretty good, 0.78, gradient boosting, 0.77. And when we add them up, we do get a bump. I think we do get a bump. So we increase that, right? Now this is just soft voting. We can actually play with the weighting and try and figure out a way to improve the score even more, right? But the idea is the same. You take 2, 3, 4, 5 very good performing models, you vote them or add them up in a way that allows you to get a prediction which is slightly more better, right? Okay, the last one. So the last one is is a slightly more meta. So it builds on the same concept of voting, but it's called stacking, in which we now take these features that have come out of our algorithm, or sorry, take our predictions that have come out of our algorithm and put a meta classifier on top of that, right? So the idea is that by doing this second level of classification, I may be able to figure out some higher order interaction that may not have been possible at the first level, right? So conceptually, this graph looks very similar to voting. The only difference is instead of that voting bucket, we now have a classifier. So we can put any kind of classifier in it. We can run another classifier on top of that, right? So we could have a logistic regression, we could have a neural network, we could have a ML perceptron, we could put another classifier there. The idea being these new predictions that have come are now a feature that goes into our classifier to further predict, right? And that is stacking. We're just stacking, I guess, one classifier on top of the classifier, right? Another classifier. 2 levels of model, right? So let's look at this again. We take the Gaussian, we take SVM, RBF, gradient boost, same as one, and now we stack it with a logistic regression, right, on top of that. When you do that, actually in this case, the stacking doesn't really help us, right? So the stacking actually is 0.73, and that's, it's not necessarily that stacking may help. It also depends on the amount of data set you have. This is a very small data set. It's also synthetic. If you try and run at about 100,000 or more data sets, and then try and run a stacking algorithm, you're likely to get much better performance and improvement based on that, right? But the concept remains the same. You can do this as stacking, and then obviously there are further refinements to it, because as we know in machine learning, we never stop. Once we figure out something, we keep turning in and tweaking it till we can find another way to improve it. So you can do much more on that, like blending and so on. But the concept remains the same. It's a meta classifier on top of that, right? Yeah?
So if we stack with some complex model, will it help in the performance improvement?
If we stack complex, so the question is if we stack complex models together or a complex model as the meta classifier? That's a good question. I don't know. My sense is a simpler classifier would perform much better than a complex classifier.
So at some stage, you have to handle outlier. I mean, it can overfit too, because you're taking predictions of one set of data and running it on another. So at some level, it can overfit. You at least don't do really complex models. For example, you don't run neural networks on as your meta classifier. You might still be fine with gradient boosting, but I think neural networks would overfit.
Yeah, Occam's razor, Occam's razor. Yeah. Okay. So whenever possible, the simpler solution is preferable. Even though I accept that as an ensemble talk, I can't really be talking about simplicity. It is inherently layering to some extent. Okay. So what are the advantages? The advantages is obviously we have seen that you can get improved accuracy because we are now able to navigate the space much more effectively. And this is all possible because of compute, right? I mean, the reason random forest and gradient boosting perform so well is because we have compute to navigate the space, which we didn't have earlier, right? They're likely to be more robust. They will generalize better. And that's our whole idea in machine learning, is how can we find algorithms that are models that generalize well, right? And you can run many of them in parallel. Not all of them, but many of them in parallel, which obviously makes it easier for you to scale this, right? The disadvantages is you're further removed from anything which is human readable to some extent. So if you want it to be explainable to some extent, it's even more harder than a normal model because you can build some intuition. You can try and do visualizations to do that. Even neural networks are being visualized as a way to try and build intuition around what's happening in them, and so that can help. But at the end, it's a little harder to make them as explainable model. They may work very well as just pure predictable one. And then what is the delta improvement you get when you put this time and effort is something that you may have to weigh off depending on your domain, right? So if you're doing fraud detection, maybe it's worth it. If you're doing telling your sales and marketing people which accounts to go after, maybe it's not worth it, right? So that time and effort trade-off would need to be made to say whether I want to spend this extra time and compute to do this, right? Where do you go from here? So we've covered the 4 basic concepts, and many of you may already be using some of them. You obviously can go to grid search for finding voting, so you build on that. So there's grid search for doing voting weights. So how do you find the weights? And you can run a grid search algorithm in it, but it doesn't scale that easily. So there are Bayesian optimization techniques like hyperopt in Python would allow you to do that, which will allow you to figure out the weights and hyperparameters given some cost function, right? So you may need to think about, can I run hyperopt type libraries on this to better understand the weights and hyperparameters, right? And then we haven't talked about one more technique in ensembling, which is feature engineering to some extent. How do I take more of these 2 features and maybe explode it to a 72 feature using a manifold, and then use that to classify? And to some extent, SVM is kind of based on that, but you can create, there are techniques like tree embedding and cluster embedding, which will give you a much larger feature space and then allow you to apply those techniques on top of that, right? It is the harmony of the diverse parts, their symmetry, their happy balance. In a word, it is all that introduces order, all that gives unity, that permits us to see clearly and to comprehend at once both the ensemble and the details. All the codes and slides are available on GitHub. It's on my repo/ensemble. I think it would be there if it's not already there in the next 1 hour, as the Git push took some time and is stuck somewhere in the middle. But it'll be there within the next hour or so. Feel free to download, raise any issue if you have questions, and come back, run the code, and see what it is. This is us, both of us. So I'm at Amit Caps. My website is amitcaps.com, and Bargava is at Bargava. So easy for us to follow if you want to. If you want to reach out to us on any of those mediums, please do that. And do we have time for questions? We can.
Okay, we actually the time's up, but I think we can maybe take just one question.
Okay, one question.
There's one question.
Yeah.
Can you guys talk a little bit about the over ensemble that we are seeing in some competitions in Kaggle, because there are so complex solutions are made in Kaggle, but these most of part of these solutions are not reproducible. So can you guys talk a little bit about this?
I think Bhargav has some strong opinions on that, so I will.
What do you guys think about this?
Okay, so now a lot of people know about ensembles just because of Kaggle, right? So but then it all depends on the kind of problem and domain that you work on. In real business settings where I work a lot with sales and marketing folks, and their interpretability is the most important thing. But as I'm told, there are applications like fraud detection, crime detection, where accuracy is very, very important rather than just understanding the interpretability. And in those instances, you would go. If you're just starting your career in machine learning, work on interpretable models, this would all come much later when you really want to squeeze the last bit out of your data. But these are really nice things that it offers, some of the nice techniques, and some of the things can help you understand neural networks better, because that is a real black box, right? So it kind of helps in getting intuition on why some things happen. So kind of things that we see in stacking is what is generalized in deep learning. So in that sense, it's good. Does it have practical applications? Very unlikely. I don't think most of the people who run the companies which run Kaggle competitions ever use those models. But it also gives a benchmark for companies. For example, if I'm running a competition, it'll give me a benchmark on how best can my solutions go with the data that I can get. So, and also if you look into just a word on Kaggle, most of the features are anonymized. You really don't know how that was formed. So it's a trade-off.
Okay, can we?
Yeah.
Oh, okay. No, so we'll take your question offline. Apologies for that. Thank you so much. Thank you so much for coming and sticking with the session. And if you have any question, Bhargav and I are around here. Happy to talk. We're also doing another talk on deep learning for text for NLP. It is really the last slot. So if you manage to stick around till then please come and attend that. It'll be really nice. Thank you so much.
Thanks, everyone.